Welcome to The Explainer. Today, we are diving deep into the monumental hardware challenge that's sitting right at the heart of the AI revolution. It's this massive bottleneck of speed and scale that could hold back the future, and we're going to break down exactly how the industry is trying to smash right through it.
So to get a sense of the scale we're dealing with, let's just start with a number. 4 trillion. That is the insane number of transistors they have managed to pack onto a single AI chip, the Cerebras wafer-scale Engine 3. It's an absolute marvel of engineering. I mean, it's basically a supercomputer on a dinner plate, built to power the most demanding AI models you can imagine.
But here's the problem. All of that incredible processing power creates a massive traffic jam. You see, as our processors get faster and faster, they end up spending more and more of their time just waiting for data to show up from memory. This growing gap, this chasm between how fast we can compute and how fast we can get the data, that's what we call the memory wall. And it's the single biggest problem threatening to slow AI's progress to a crawl.
Okay, so here's our game plan. First, we're going to look at AI's just unbelievable hunger for computation. Then we'll dive into the fight against that memory wall, looking at solutions both on the chip itself and then zooming out to the whole data center. We'll compare the two leading philosophies for building AI hardware, and finally, we'll take a peek over the horizon at what's coming next in the computing revolution.
First off, let's just try to grasp the sheer scale of this. The size of AI models is just exploding. We've gone from millions of parameters to billions, and trillions are right around the corner. To keep up, the amount of computational power needed has shot up 1,000-fold in just 2 years. Now, to put that into perspective for you, that growth rate doesn't just bend Moore's law, it completely shatters it.
So all that enormous demand puts this immense pressure on the memory that's sitting right next to the processor, and it's forcing engineers to get incredibly creative. I mean, right down at the microscopic level, rethinking the very foundations of how a computer's chip even works. And here it is. This is the whole problem in one simple chart. For decades, processor performance has been on an absolute rocket ride, getting exponentially faster. But memory bandwidth, that's the speed we can actually feed data to those processors. It's improved at a much, much slower rate. That widening gap you see right there, that is the memory wall in action.
And, this problem exists right on the silicon itself. The super-fast on-chip memory, called SRAM, which is crucial for caches, is hitting a scaling wall. As chipmakers keep shrinking the transistors for logic, the 6-transistor design of those SRAM cells just isn't shrinking at the same pace. And what that means is memory is taking up a larger and larger chunk of the chip, creating this huge internal bottleneck.
So here's a radical solution. What if you just stopped moving the data altogether? That's the wild idea behind in-memory computing. Instead of constantly shuttling data back and forth from memory to processor, what if the memory could just do the computing itself? New designs are coming out that use novel SRAM cells to perform calculations right where the data is stored, completely sidestepping the memory wall.
Okay, so another tactic? If you can't move the data faster, just make the data smaller, right? Advanced hardware-accelerated compression can effectively double or even quadruple the amount of memory you have available on a chip. Take NVIDIA's latest Blackwell platform, for example. It has a dedicated decompression engine that can unpack data at a blistering 800 gigabytes per second. It just feeds those hungry processors without missing a beat.
Now, these on-chip tricks are brilliant, they really are, but they only solve part of the problem. You see, modern AI relies on these massive systems with hundreds, sometimes thousands of chips all working together. So what happens then? What happens when you need to connect all of those chips and all of their memory together?
And that very question takes us from the individual chip out to the entire data center. And out here, the problem isn't just speed, it's waste. We find these vast amounts of super expensive memory just sitting there, completely unused or stranded, because they're locked inside individual servers that aren't being fully used. Think about it. In today's data centers, adding more memory is just ridiculously expensive. If you need more DRAM for a CPU, you often can't just add the DRAM. You have to buy a bigger, more complex, and exponentially more expensive server just to hold it. And with memory becoming a huge part of a server's cost, that model is just, it's not sustainable. But there's a new technology emerging that is completely flipping the script on this. By decoupling memory from the server itself, data centers can get the same memory capacity for, get this, about 55% less cost per gigabyte. That's not just an improvement, that is a total game changer for system design.
And this is all made possible by something called Compute Express Link, or CXL. The easiest way to think about it is like creating a shared public utility for memory. It's an open standard that builds this high-speed highway between all the processors and a massive shared pool of memory that any of them can access whenever they need it. So all this new flexibility in connecting things, both on the chip and across the data center, has led to two giant, competing ideas for building the world's most powerful AI systems. And it really is a clash of architectural philosophies. On one side, you've got the monolithic wafer-scale approach championed by companies like Cerebras. Their philosophy is, let's build an entire AI supercomputer on one single massive piece of silicon. That way, you eliminate the communication bottlenecks completely. Then, on the other side, you have the modular approach from NVIDIA. They connect an army of thousands of powerful individual GPUs into a massive flexible cluster using these high-speed links.
And this table really highlights the fundamental trade-off, doesn't it? These wafer-scale systems from Cerebras offer just a staggering number of cores all on one integrated unit, giving you on-chip bandwidth that is just unparalleled. But in contrast, the GPU clusters from NVIDIA offer incredible flexibility and a really mature software ecosystem, but they're always fighting the physics of communication latency. So it's a choice: integrated power versus modular scale. You know, this race to rebuild computing from the ground up, it's pushing us into completely new territory. And while that brings incredible opportunities for innovation, it also, well, it creates new and totally unexpected risks.
For instance, a design choice that was actually meant to improve power efficiency, separating a chip's power supplies, has accidentally created a new security flaw. It's called the volt boot attack, and it basically lets someone with physical access to the chip manipulate these power domains to keep sensitive data in SRAM from being erased during a reboot. It just bypasses a whole lot of security measures.
And the solutions that are coming up on the horizon, they look like something straight out of science fiction. We are talking about 3D integration, literally stacking chips vertically to bring memory and logic closer than they've ever been. We're looking at photonics, using light instead of electricity for near-instant communication. We're even re-engineering the transistor itself, all while building in advanced error correction to make sure these tiny new structures are actually reliable. So ultimately, what you should really take away from all this is that we are witnessing a fundamental shift. We are moving way beyond just making computers incrementally faster. We are now redesigning them from their most basic elements: the transistor, the memory cell, the very connections that bind them all together. The engine of AI is being rebuilt from the silicon up. And the question it forces all of us to ask is no longer just about speed, but about fundamentally reimagining what a computer can and what it should be.